Let's talk briefly about extending a function or creating extended functions. So we tiptoed around this in class, but I think it'll be better for us to take it head on. An extended function, you can see that's defined right here. Oopsie, that's not right. An extended function is a function that is obtained after a discontinuity is removed. All right. So in other words, we are dealing with removable discontinuities, meaning that we're going to plug the hole. To write an extended function, find the hole, right? So you're finding the hole, and then write a piecewise function to fill in the hole. That's our job. Okay, so your strategy for doing this is simply to do the limit and then write the piecewise function. So the step one, I'm going to do a limit. And then step two is I'm going to make a piecewise. So let's see if I can do that with letter A here. I might not do both examples in this video, but I'm definitely doing letter A, and I got a couple of other specific examples to show you on the other slides. So for this slide, I'll just do letter A. Okay, so step one is I want to do the limit. Now, which limit do I do? That's funny. Which limit are we going to try and evaluate? Well, we want to remove the discontinuity, so the discontinuity takes place at x equals 1. So the limit that I'm going to work on is the limit as x approaches 1, because that's where the discontinuity is, right? I find that by the zero denominator of the function. So I'm going to do the limit on this function f of x as x approaches 1. So you always try substitution first. When I put a 1 in, something bad should happen because we know it's a discontinuity, but let's see if something good happens. We plug a 1 in, and that's a 1. So I get 1 minus 6 plus 5, and on the bottom I get 1 minus 1. So that turns out to be 0 over 0. Well, that's great news. That means that we have an indeterminate form. It means we probably can figure out what the limit is. Okay. And of course, since we're doing these extended functions, you know we're going to be able to do the limit. In this case, our strategy should be to do factoring and canceling. So we're going to factor the numerator. I think that's just x minus 1 and x minus 5. And then the denominator, of course, has an x minus 1. So we can cancel the x minus 1s and then do substitution again. And this time we get 1 minus 5, which I think you'll agree is negative 4. So our limit as x approaches 1 is negative 4. So here's how we fill that hole. We make a piecewise function, and I'm going to have to squeeze it in here. I'll call it g of x. I'm making a new function. This is the extended function. My function is going to equal f of x, the same old function that we had before. And since we have f of x defined up here, I don't need to rewrite the whole thing again. I'm just going to put f of x there. And that will happen when x does not equal 1. As long as x isn't 1, this function is perfectly fine. It's just that it has a hole in it. And we want to plug the hole so we have continuity. So that means when x equals 1, this should, I guess, just say if there. If x equals 1, then we want our answer to be negative 4. And this piecewise function, which I squeezed in on the screen here, I should have used my screen a little better. But this piecewise function is the extended function that we want. It's extended, and it takes care of the hole. Everywhere except 1, we stick with the same old function, f of x. But when x equals 1, we want it to equal the limit. We want the dot to be in the hole instead of either non-existent or somewhere else. And so that's an extended function. I obviously don't have room for letter B here, so I'm not going to cover that on this slide. But that's how we do an extended function. Let me show you a couple more examples just so that when you're working on the homework, you'll have an idea of how to attack these. So consider the function h of x, where h of x is sine of 7x over 2x. And again, we can see that there's a 0 in the denominator, right? Which is our point of discontinuity. And so what we want to do is we want to take the limit as x approaches 0 so we can fill the hole. So I'll write out the limit, that's step 1. The limit as x approaches 0 of sine of 7x over 2x. And we've been practicing these recently, so you know that our goal is to get sine of 7x over 7x. That means that I have to multiply by 7x down here so I can get it underneath, but if I do that, I have to multiply by 7x up here as well. And then I'm just going to rewrite this thing so we can see how this limit's going to work out. There's going to be two parts to the limit. I'm going to have the 7x on top that I put in, and I'm going to put that over the 2x. And then I'm going to multiply that by the sine of 7x over the 7x that I put in on the bottom. And then we just do a little bit of simplifying here. Here we cross out the x's, and so this part of the limit is 7 over 2. And we know from our theorem that the limit of sine of 7x over 7x as x approaches 0, because 7x is going to 0 also, this turns into a 1. So this whole limit is 7 over 2. Okay, step 1 was to solve the limit, and we've done that. What we're saying is we want the point to fill the hole to be at 0, 7 over 2. So now let's do the extended function. I'll make a new function. Let's call it g of x again. G of x is going to be h of x whenever x does not equal 0. Right? As long as we're not 0, we can just use the function. It works perfectly fine. But when x equals 0, we want our answer to be 7/2, our y value. So we'll say if x equals 0, we're going to use 7/2. And again, this thing is called an extended function. We filled the hole in the original function. Like if you graph this function on Desmos, you won't even see the hole, but there's a hole at 0. It'll just look like it's at 0, 7/2 on Desmos. Hopefully this helps with one of the homework problems, and then I've got one more example, and then we'll shut this video down. So let's consider this function x minus 9 over the square root of x minus 3. And I think you'll agree that this function has issues at x equals 9. When x equals 9, we've got a problem because we get 0 in the denominator. There's a discontinuity there. So our job is, step 1, we're going to do the limit as x approaches 9 of x minus 9 over the square root of x minus 3. Now, when we plug 9 in, remember, we do get 0 over 0, so that's an indeterminate form. It means we can find the limit, probably. So we're going to keep doing math. Let's do something weird here. Even though it doesn't look like it, we can consider x minus 9 a difference of perfect squares. And if we can consider it that, we can factor it. So instead of the limit that we have on the left here, let's write a new limit. And I'll factor this x minus 9. Basically, I'm just going to have the square root of x here plus 3 and the square root of x here. Oops, that's supposed to be an x. Square root of x here minus 3, right? Square root of x times square root of x is x, so I can consider the x a perfect square as long as I can take the square root. And that's good news because I have the square root of x on the bottom here. And you'll recall that we can cancel these out using algebra. And now when I do substitution, the value of this limit is 3 plus 3, which is 6. Right? The square root of 9, if I plug 9 in there, it's the square root of 9, which is 3, plus 3 is 6. So I'm going to fill the hole with 9, 6. Then you write your extended function. We'll call it g of x again. We might as well be consistent here. Something in the world's got to be consistent these days, and that's going to be that I'm calling my extended functions g of x. Okay. As long as I'm not 9, I can use my regular old f of x function. F of x is perfectly fine for everything except 9. So for x not equal to 9, I'm going to use f of x. But if x equals 9, I want to use the y value 6. I'm going to plug the hole. And now I have an extended function, right? We'll put a green circle around it, or rectangle, because that's what I've been doing lately. This is extended. And now this thing is continuous. That's the most important part, that we filled the hole with 9, 6 so that this function looks like a continuous function. And like I said, if you graph this on Desmos, it's going to look continuous. It's going to behave like the square root of x plus 3. And because Decimals doesn't show the holes until you put them in. So, okay, that's extended functions. It's really not that bad. Give it a go, and then we can talk when we see you again. Take care.